very quickly, my two obligatory corporate requirement slides. For anybody who doesn't know who Alstom is, we're in everything that's in power and trains. I'll leave it at that because that's not what you want to hear. And we're sort of all over the U.S. We're in more than 50% of the power plants. We dispatch 40% of the power flowing through the system on our software. And for those who like subway cars, particularly in Washington, 6000 series are ours. What I want to talk about, what I've been asked to talk about, is the existing fleet. And the first statement, I think I don't have to tell anybody, it's critical, but I want to talk for a few minutes about why. And will it be base loaded? Are we going to cycle it? And the answer is pretty straightforward. You're going to see it has to be base loaded. I'm using EIA data for this, and it considers NSP, but it does not include 111D. So bear in mind what I'm going to talk about does not include that. But the important thing is we're talking about a fleet that is going to get old, and let me show you that, which is actually expected, according to EIA, to produce 125% of the terawatt hours in 2040 that it produces today. That's a pretty interesting statistic. It's pretty interesting how they get there. And that's what I want to talk about for a couple of minutes. Okay, I want to credit Ken Kern and his great guys at NETL for a lot of really interesting analysis, and they let me borrow a couple slides, just to set the stage of what we need to do with this fleet. This is just a profile of both, in this case, it's both nuclear and coal, when it was built. And, what we're talking about is substantially this fleet is going to get 27 years older from today, and it's got to keep running. You'll see the retirements are all projected in the next couple of years, and the rest of the fleet keeps running. That's the basic assumption. 56 gigawatts less. And we don't build new coal, because that's part of the projection in this, because of NSPS. There is no new coal. So, also, I should mention the box in the lower right. We don't really retire anything after 2020. The average of the fleet becomes 62 years old in 2040. And that's what we're going to run, a 62-year-old average fleet. So what gets more interesting about this is if we look at the history of running our plants, this is the history of capacity factor with age. And if you'll notice, you get out around 60 and it becomes pretty low. So let's apply that then as good folks at ATL did. Let's look at that compared to the EI forecast. Well, okay, put the curve in because we got to take the curve to the next slide. Okay, we have it sitting out here. This is the capacity factors that EIA came up with for the fleet to achieve those terawatt hours. They backed it down from 78 to 73. 73% capacity factor for this fleet. There's the historical capacity factor for the fleet for the last 15 years. It's only 64%. Magically, though, we're going to get to 73 out of this fleet at age 62. Let's look at how we think old plants work. And that tells us the weighted average for this fleet should be 28% capacity factor. So we have a problem. And the problem is, how do we sustain this to achieve 73%? So it becomes absolutely imperative that we maintain and actually improve the existing fleet if we're going to do what we have to do by at least EIA's interpretation of the regulations. And frankly, you can argue with them, but there's still not too many people that say we're going to build coal with NSPS. So unless we get something else that happens, what do? The good news in my mind is we have the technology to improve and sustain this fleet. We can do almost anything to these existing plants. We've developed retrofit technologies, whether you want to baseload or cycle. And frankly, I I guess, outside reviewers of the report that you guys all just adopted. And I think, we're in a position to address all these issues technologically, and that's an important piece. However, and I'm going to be a little more tactful than Fred was in his, we need a proper, supportive regulatory agenda if we're going to do this. And I'll get some more of that at the end of the talk, but, this is where we are. So, we got to talk about plan optimization. And plan optimization actually starts with fleet optimization. You move down to plant. You go from plant to subsystems in the plant, and eventually we get down to actual components. And that's what we really have to do if we're going to get there. Performance improvement, the big headings, reliability and availability. How do we get to these issues? Because as we just said now, we have to be able to rely on this fleet at a 73% capacity factor. It's impressive. And we need to improve the performance if we're going to get there. And we'll accomplish a great deal if we can. And you see, I'll go through more detail. Again, addressing efficiency, parasitic load, and parasitic load has become associated with CCS, but the reality is there is a parasitic load in every power plant because there are always pumps, fans, everything that do not contribute power but take power to run. So we need to minimize it. Flexibility, regulatory, because we've got not just emissions, but how do we get to the cooling issues, the water issues. I mean, these are going to be equally important on these plants. And as was said by Fred, these things weren't built for CCS. Many of these plants weren't built for big water systems and treatment systems. So, but we're going to keep running them and find a way. Okay, and then under reliability and availability, again, gets into, whether we're going to design these plants for maximum revenue, which a lot of utilities want, or minimum outage. Okay. First, we got to start with an energy assessment, which is both thermal performance and energy. And this is very simply, an energy assessment begins with really looking at all the things we can do to improve the thermal performance, to upgrade these things, to maximize in the heat cycle. Okay? It starts with an energy and economic evaluation. Look at the design basis. Look what we can do. Use plant instrumentation. You need to interview the plant staff. How do they actually run these plants? Because while we can, as an OEM, we can build something, but how the customer, just like with everything else, GM can build a car, but we all run it differently. And we can build boilers, we can build them similarly. We can build steam turbines, but it doesn't mean our customers run them the way we said to run them, because things change. We need to look at results, design heat rate comparison. I'll talk a little bit more about that in a minute. Then operational adjustments to get some short-term results. And then, find solutions that really amount to dollars per BTU per kilowatt hour. Because at the end of the day, we got to be profitable. We can't just do these things. It's nice to say we want to sustain the fleet because we have to make electricity, but we also need to be conscious of the impact of the cost, because we've been involved in a lot of discussions recently with people like NARUC and PUC commissioners, and their whole thing about approving things is keeping the cost of electricity from going up. And that's where I think you're going to see a real butting of heads with the regulatory things, that we have coming out, CO2, and the public utility commissions in the states. What can they really do? How do they, because those people have to run for office. And so they're conscious of, as Julio said, CCS is an 80% increase in the cost of electricity. How do you deal with that and get reelected? It's a really interesting question. Anyway, that's not my question though. So, how do we find programmatic and best-in-class solutions? And this is just a long process. It's for some people a tedious process, but it's an absolute necessity. Here's a case in point, and this is a particular unit that can be nameless, but you'll see how the heat rate has degraded, and you'll see where it's degraded. A large in turbine performance, and this is true in most plants. And this is not only something we can recover, but I'll talk more, we can do better. because we have better turbine designs today, better blading and things than ever before. So there's a huge potential pickup here. Boiler performance, condensers, the whole business, it all contributes. So what you do is basically, in your assessment, we prioritize our recommendations. And you'll see the investment, annual savings, and you go through this, and it turns out that this is all makes sense to do today, even for people who aren't doing this, because you can't get the money back if you can't get past the regulatory scheme. But it's going to be required if we're going to keep this fleet running, and if it's going to be efficient, and if we're going to maximize the amount of electricity from a diminishing fleet. So this is the eye chart. We can do all this stuff, which is just about everything. We can just, as long as you keep the walls of the power plant, we can literally replace everything inside it. And that has happened. I always point out one of my favorite plants in the world. I'm from Philadelphia, Pennsylvania originally. For those of you who know the Schuylkill station, it went online in 1904. It's still a steam cycle, pretty interesting. The brickwork's original. I don't know how much of the rest of it is, but the point is, we can sustain the fleet, and that's really my message. So we can do all of this stuff. And it gets into, obviously, the boiler cycle, the steam cycle. All of these things contribute depending on the plant and depending on what needs to be done. On the auxiliary power, and this is the negative, and you'll see is the equation at the top, the boiler efficiency, steam cycle efficiency, and you subtract the auxiliary power. This is the original parasitic load before CCS came along. So many things that we can do to keep the fleet moving. Here's some specific, and these are newer technologies. Obviously supercritical and ultra supercritical. We can upgrade plants. Turbine upgrades, this is a particularly, good subject. There's so much technology that's of recent vintage in steam turbines. So there's a lot of opportunity here, and you can go down this. Obviously condenser designs, cooling tower designs. A big one are control systems. Much better control systems today than most plants have. And it's always kind of interesting if you go in a few plants, some of the older plants, and you'll literally see the new control system, if they have one, sitting on top of the old one. Or it's always kind of fun to see a new system and a unit next to it with the old system, with the dials and the cranks and all that kind of stuff. So big way that we could save money. Boiler design changes to reflect current operation, whether it's changing actually in terms of cycle, but we can actually bring it up to, obviously we have better design for tubes for heat exchange. So pulverizers, again, dynamic classifiers, air heaters with less leakage. There's lots of things we can do. So essentially, it gets down to balancing the system. Turbine retrofit, boiler retrofit, and environmental retrofit. And we can retrofit everything on the back end. And one of the things, and I really didn't put it in the slides, but one of the biggest things that we're experiencing right now is electrostatic precipitators. There are relatively few fabric filters going in for mats because we're finding upgrade of electronics with the improved TR sets and things can take an existing precipitator and take it to not only the new levels, but the levels that are going to be required under the PM NACs. So these are really important and cost-effective ways, because again, you get into the instance of, how do you tear down an electrostatic precipitator and build a fabric filter? We all don't kind of have the luxury in plants of building it one behind the other. So how do you accomplish this? And I will tell you, because we've done them, the idea of retrofitting a fabric filter into an existing ESP is a really interesting technical challenge. It can be done. But, if you can get it with electronics, and we're finding more and more people can, this is the way to go. We can upgrade SCRs. We can keep SCRs hot now, even on reduced load. So we can do these things and sustain it. We can maintain the environmental integrity while we do these others. It's a balance. And it's always been the concern that if we do the first two, we then have the potential to actually burn more fuel. So we've got to have the back end upgraded to match what we can do on the front end. because frankly, it's a little disappointing if we upgrade the front end and then run it at less capacity because of a permit. So we really need to upgrade. Optimized retrofit objectives. Obviously, we want to maximize the potential of the existing asset, and whatever that means in terms of upgrading the steam turbine, upgrading the boiler, bring it back to its original generating capacity or exceed that. Increase in just heat rate and efficiency, and that has simple benefits that I'll show you in a minute. Assess the balance of plant. Balance of plant is a very costly item in power generation, and we've really got to assess it and see where we can make improvements, and that's the whole of the water system, all the auxiliaries in the plant. Reduce relative emissions with efficiency. Again, we can upgrade all of the back ends. There's nothing, I don't believe there's anything that can't be brought into to a level, even where we're burning more fuel. So, but if we're going to do this, I think we have no choice. There's always a choice, but this is the simple thing. We want to address CO2, and this is kind of the message that we've been trying to get across to EPA. Efficiency reduces CO2. It's a really simple graph, and it's a really simple reality. We go to ultra supercritical for new plants. We can push CCS out. If we go to the most efficient plants that we can build on the new side, and we do the things that we can do with the existing plant, we can well exceed the initial goals for 2020, that, the President's original goals. I think we're going to get some new goals, but I'll talk about it in a minute. But we can meet or exceed those goals and give us the time to really bring CCS to the market at a price that's affordable and a system that we have confidence that works. And more importantly, since I'm an OEM, that we can give guarantees of performance, because that's really the ultimate game. Nobody wants to buy a car with no guarantees. Nobody wants to buy a piece of power equipment with no guarantees. So, while we accomplish everything else, like I said, all the things that we can upgrade, all the things that we can bring in compliance, we can do all of that. And we're going to get CO2 reduction. It's like magic. Get this for free, just because we want to sustain the fleet and we want to make it more efficient. We actually reduce CO2. Interesting concept. Again, one we're selling. So, my last slide, and now I'll sort of preach, but this was written by EPA. They know NSR is a mess. They know it's wrong. So now you're going to have two opportunities in June. You're all very lucky. I was assured a week ago, June 1st, we're going to see the 111D proposal, okay? On June 24th, we're going to see the rule for modified and reconstructed plants under 111B. Surprise rule. It went to OMB on April 24th, if anybody wasn't watching, and most people were not watching. I personally can say that I found out about it on a telephone call. We were having a meeting with EPA. They had the guys from RTP, they were trying to get on the phone. They couldn't get on the phone. Why not? We have to finish this rule. What rule? Recon. What's recon? It's a 111B rule for reconstructed and modified plants. And it went to OMB on April 24th, and it will come out of EPA on June 24th. That's the schedule. So we're going to get two chances to really try to hammer the issue, I think, of NSR. There's a rumor, and this is Washington, so we live on rumors. And there's a rumor that part of the recon, because there are no recon plants or reconstructed modified plants. There aren't any until they trip NSR. Okay, so right now that rule's coming out, and there are no plants that it governs. So we're trying to figure out, why are they doing this? So there are two really good rumors. So, one, maybe they're going to address NSR, because that would be logical in a rule on reconstructed and modified plants. And boy, that's exciting to think. The second one is there are people who think the original NSPS rule is in trouble, legally or however you want to put it, but they need a 111B rule to sustain their momentum on a 111D rule, because that's the way the system works. So the idea is if you put out a very simple, reconsidered, modified rule under 111B, you have something that hopefully can sail and catch up, and it can sustain the momentum of 111D. So enough of my rumors. But all I'm saying is what I really encouraging everybody, we need something to happen here. All the good stuff that we can do, all the good stuff that has to happen, you know, if we're going to make the terawatt hours that everybody thinks we're going to make with this existing coal fleet in 2040, or frankly, even before 2040, we've got to be able to do the things we need to make this fleet efficient, to get CO2 reductions, to do all the wonderful things that we know we can do. At least I think they're wonderful. So I just encourage everybody, tell your friends, tell your relatives, whatever. You got 2 chances to comment here that should focus on, 111D and a recon rule. So, please join the choir, whatever. We need to do something, and I think it is incumbent on this industry to bring this story, and we've been giving this story to EPA, and they're actually starting to get it. I really believe in a couple of meetings they are getting this, so I'm really saying, we need a bigger chorus, and I know that NCC can't do this, and I'm speaking to you as individuals, not as NCC. We need to do something, and we need to do it. So with that, I thank you. We can sustain the fleet. We have the technology. We just got to get it, and we got to get the regulatory atmosphere that allows us to do it. And it's a brave new world. The idea of the average plant being 62 years old, geez, it's like me. I wish I could do what I could 27 years ago, So maybe I should say my wife does too. But anyway, enough of that. So thank you very much for the opportunity to talk.
Thank you.